Question 12.1, define simple harmonic motion. 2, derive an expression for the time period of oscillation for a mass m attached to a vertical spring of force constant K. In order to understand these two questions in more detail, you can see my lecture video of vertical mass spring system. The link is added on the description. Now let us go for this, okay? And we know the time period of vertical mass spring system is T equals twice pi under root m by K. So this is the time period of vertical mass spring system. Now let us come to this part, okay? What will be the time period if this system is taken inside the satellite? Okay, so we can write for artificial, or we can simply write man-made satellite, okay? What do you find? Inside the artificial satellite, okay? So what do you find? The body is in condition of weightlessness, that is z equals 0. So we find this inside the man-made or artificial satellite. Now what do you find? We find, let us call it equation 1. We find equation 1 is independent of g. Therefore, there will be no change in time period, okay, if the system, that is the vertical mass spring system, if the system is taken inside, okay, the satellite. By satellite we mean man-made satellite, okay, or artificial satellite. So we have this, okay. Question 13a, state Bernoulli's principle. To understand Bernoulli's principle, you can see my lecture video on Bernoulli's equation. The link is added on the description. Now 13b, figure below shows a liquid of density 1200 kg per meter cube flowing steadily in a tube of varying cross section. The cross section at point A is 1 centimeter square and that at B is 20 millimeters square. Points A and B are in the same horizontal plane, okay? So we need to note this. A and B are in the same horizontal plane. The speed of the liquid at point A is 10 centimeter per second. Calculate 1, the speed at B, 2, the difference in pressure at A and B. Now, we know liquid is incompressible, okay? So the density, okay? Density, rho is constant and density is 1200 kg per meter cube. So we must note that density of liquid is constant. So this is to be noted. Is flowing steadily in a tube of varying cross section. We can see cross section at A, okay? Cross section at A and cross section at B is not same. So I'm writing CSA, cross-sectional area at point A. So this is AA, and this is 1 centimeter square, and we need to change this, okay? 10 to the power minus 4, okay, meter square. So we have this. We must change the given quantity in SI system, okay, wherever necessary. And next, cross section at point B, let it be AB, and this is 20 millimeter square, and we use this conversion, okay? 10 mm equals 1 centimeter, and we know 100 centimeter equals 1 meter. So using these two relation, okay, we finally get this 20 into 10 to the power minus 6 meter square. So we have this. Now the speed of liquid, okay, speed at A is, let's say, VA, and this is 10 centimeter per second. So 10 into 10 to the power minus 2 meter per second. So we have this. And we are asked to find, okay, speed at B is VB, and this is to be determined, okay? So case first. Okay. Now let us come to this, okay, sentence or line. Point A and B are in the same horizontal plane. So I'm drawing a reference level, okay? So this is a ground. Now what we find, if A and B are in the same horizontal plane, then height or elevation of point A equals the height of point B. So what we find, so I'm writing in this way, okay? From question, okay, we have this. A and B are at same height. Therefore, YA equals YB. So we find this. So this is to be noted, okay? Now, first we need to find the speed at B. To find VB, we use equation of continuity. An equation of continuity states that the product of area of cross section times the speed is constant. So this is called the equation of continuity, okay? This is the mathematical form of equation of continuity. So AA, VA, we are applying equation of continuity at point A and B, okay? So this equals AB, VB. Therefore, we can write VB equals AA by AB, and we have VA. So we get this, okay? Let us call it equation 1. Now, let us put the values in equation 1, okay? AA is 1 into 10 to the power minus 4 by AB is 20 into 10 to the power minus 6, and VA is 10 into 10 to the power minus 2. So we have this, okay? we have 5. So we get speed at B is 0.5 meter per second. So we get this. Okay. Next, we are going to find difference in pressure at A and B. So we are going to find this. Difference in pressure at A and B. So for this, we use Bernoulli's equation, okay? Now we know PA plus rho G YA plus half rho VA square equals PB plus rho G YB plus half rho VB square. And we can see, okay, the second term on left hand side and the second term on right hand side, okay, cancels each other. Why? Because A and B are at same height. Okay, therefore we can write PA plus half rho VA square equals PB plus half rho VB square. PA minus PB equals half rho VB square minus half rho VA square. So we can take half rho common. So we can write VB square minus VA square. Okay. So we have this. So we have this. Therefore, we can write PA minus PB equals half rho. Now we know VB square, and from equation 1, okay, we can write in this way: AA by AB whole power 2 and VA square minus VA square. Okay, so we find, okay, this by using 1, okay, using 1. Now we can write PA minus PB equals half rho. Now we have AA by AB whole power 2 minus 1, and we have VA square. So we have this. Now using this equation, okay, we can find the difference in pressure at point A and B. So I'm erasing this, okay. Therefore, from equation 2, okay, PA minus PB equals half density, okay, rho is 1200 kg per meter cube. So we have this, and AA is 1 into 10 to the power minus 4 by AB 20 into 10 to the power minus 6 and whole power 2 minus 1, and VA is 10 into 10 to the power minus 2 whole power 2. Now let us find the value of, okay, inside the square bracket first. Okay, let us find the value of the term inside the square bracket. So we get this, okay, 24, and this will give me 600. Okay, and this will give me 0.01. Now let us so we get this, okay, difference in pressure is 144 and the unit is Newton per meter square. Therefore, PA minus PB equals 144 Newton per meter square. So we have this. Okay. Question 14a, draw a PV diagram of petrol engine and explain its working based on its PV diagram. So you can check or see my upcoming video for question 14a. Now let us discuss question 14b. Compare the efficiency of petrol engine with that of diesel engine based on their compression ratios. So we need to note this, okay? Now for petrol engine, or we can also write in this way, okay, for auto cycle, petrol engine or auto cycle, okay, auto cycle efficiency, I'm writing in this way, okay, eta P, this equals 1 minus 1 by R whole power gamma minus 1. Let us call it equation 1. So this is efficiency of petrol engine or auto cycle. Now R is the compression ratio, gamma, okay, this is ratio of heat capacities. In some text, okay, we find symbol rho used for representing, okay, compression ratio. So we are using the symbol R, okay, for representing compression ratio. Do not get confused, okay? So now what we find in actual or real practice, okay, for petrol engine, R cannot be greater greater than 10. The value of R, that is compression ratio, cannot exceed 10. Now, if R is greater than 10, okay, then the mixture, okay, mixture gets ignited, okay, it burns by itself due to compression much before, okay, that is earlier, too earlier, much before ignition takes place. So we find this, okay, so this is to be noted, okay. Now, for diesel engine, efficiency, so I'm writing in this way, eta d, this equals 1 minus 1 by gamma 1 by r whole power gamma minus 1 rc square minus 1 by rc minus 1. So I'm rewriting, okay, this equation in this way, okay. Efficiency of diesel engine, this equals 1 minus 1 by r whole power gamma minus 1. So I'm using a square bracket, okay, and writing 1 by gamma rc square minus 1 by rc minus 1. So I'm writing in this way, okay. Let us call it equation 2. So equation 1 gives the efficiency of petrol engine or auto cycle, whereas equation 2 gives the efficiency of diesel engine. Now, in equation 2, okay, and this equation, okay, R, this represent compression ratio, and RC, okay, this represent or is called Kirchhoff ratio, okay, it is called Kirchhoff ratio, or is called combustion expansion ratio, or is called combustion expansion ratio. Now, if we compare, okay, 1 and 2, so what do you find from 1 and 2, okay, what do you find when you compare 1 and 2? We find for given R, that is if R is constant, okay, or if R is same for both petrol and diesel engine, that is if R is constant or has same value for both petrol and diesel engine, we find given R, okay, efficiency of diesel and efficiency of petrol, okay, differ only in the term, okay, that multiplies 1 by, we can see, okay, R whole power gamma minus 1, we can see, okay. We have this, okay, and we have this. Okay, so what do you find? In equation 1, the term that multiplies this 1 by r whole power gamma minus 1, okay, is 1. So we have 1. And the term that multiplies 1 by r gamma minus 1 is this. So this is the term that multiplies, okay, 1 by r gamma minus 1. So we find it, okay. Now, what do you find? For petrol engine, okay, for petrol engine, okay, what do you find? The term, okay, as I said earlier, the term that multiplies 1 by r gamma minus 1, okay, the term is 1. See, we are talking about this, the term that multiplies, okay, so the term is 1. For diesel engine, okay, the term is, we have this, okay, the term is this, we have this, okay, the term is this, the term is 1 by gamma, okay, and we have rc square minus 1 by rc minus 1. So we have this. So we find this, okay. Now what we find is that gamma, okay, and rc, gamma and rc, okay, are greater than 1. So this is to be noted, okay. So this is to be noted. So gamma and rc are greater than 1. So if it is greater than 1, so I'm erasing this, okay. This is for diesel, okay. So let's come over here. So as I said earlier, gamma and rc are greater than 1. Therefore, okay, 1 by gamma rc square minus 1 by rc minus 1, okay, this is greater than 1. So this is to be noted, okay. So it is greater than 1. Therefore, or so we can write, okay, for same value of rc, okay, so for same value of rc and taking ideal gas as the working substance, okay, taking ideal gas as the working substance, efficiency. So what do you find when we look or compare equation 1 and 2? What do you find? Okay, efficiency of diesel, since this is, okay, this term is greater than 1. So what do you find? Efficiency of diesel is less than efficiency of petrol engine, okay, for same value of rc and taking ideal gas as the working substance. Keep in mind, okay, if we take ideal gas as the working substance, then efficiency of diesel is less than efficiency of petrol. This is, okay, with reference to this condition, okay, that is for same value of RC and taking ideal gas as the working substance. Now what do you find in real practice? Okay, so I'm erasing this. What do you find in practice? Okay, in real practice, for petrol engine, what do you find? RC lies between 7 to 9. Okay, it lies between 7 to 9. So I'm writing in this way, let's say 7 to 9. And for diesel engine, okay, RC lies between 15 to 20. It lies between 15 to 20. So what do you find? Due to high, since we are asked to compare the efficiency of petrol engine with that of diesel engine based on their compression ratio. So this is to be noted, okay, in practice, okay, due to high compression ratio, actual diesel engine, okay, real diesel engine, actual diesel engine, diesel engine have actual diesel engine have higher efficiency than petrol or auto cycle. So this is to be noted, okay. So we need to note this point, okay. So this condition is applicable only for the same value of RC and taking ideal gas. So this is to be noted, okay, taking ideal gas. But in real or in practice, we find, okay, efficiency of diesel engine is greater than efficiency of petrol engine, okay. Why? Due to high compression ratio of diesel engine. Question 15a, when the wire of sonometer is 75 centimeter long, it is in resonance with tuning fork. On shortening the wire by 0.5 centimeter, it makes 3 beat with the same fork. The beat is the difference in frequencies. Calculate the frequency of the tuning fork. So we are going to use this concept, okay. Tuning fork and wire of the sonometer is in resonance. So in order to find the frequency of tuning fork, okay, we compare it with the frequency of wire of sonometer at resonance. And we know for vibrating string fixed at 2 inch, okay, fundamental frequency or lowest note is F equals 1 by 2L under root T by mu. So we have this, where T is tension, L is length of the wire, okay, and mu is mass per unit length, okay, of the wire. So this is the fundamental frequency of the wire of sonometer, okay. And what we get for constant T and mu, frequency is inversely proportional to length. So we have this. So what we can write is that, okay, if L decreases because the wire is sorted, okay, on shortening the wire, if L decreases, then F increases, and if L increases, then frequency decreases. So from this equation, okay, from this equation, we can write F times L equals constant. So we have this. Now, let's call it equation 1. Now from equation, okay, from equation, L, okay, is 75 centimeter, and let F, okay, this is frequency corresponding to length L, and on shortening the wire by 0.5 centimeter. So L dash, this is 75 minus 0.5. So this gives 74.5 centimeter, and let F dash, okay, F dash. So what is this? This is frequency corresponding to length L dash, that is decrease in length. So now using 1, okay, we have this FL equals F dash L dash. So we have this. Now, as I said earlier, okay, as I said earlier, when length is decreased, then frequency increases. Therefore, what we write is that F dash, okay, this equals, because F dash is greater than F. So we have this. So F dash equals F plus 3, because 3 is the bit given, okay. So we have 3 bits with the same fork, and bit is the difference in frequency. So we have this, okay. So what we do now, from this equation, okay, F L is 75 equals F dash is F plus 3, okay, and L dash is 74.5. okay. So we are using this, and from this equation we can write F dash minus F equals 3, and 3 is the bit, okay. So as we know, bit is the difference in frequencies. Now on rearranging, okay, now let us find this ratio, okay. So we get this f plus 3 divided by f equals 1.006. Okay, so we get this. So f plus 3 equals 1.006 times f. Therefore, we can write 1.006 f minus f equals 3. So we get 0.006 f equals 3. Okay, we have this. Now f equals 3 divided by 0.006. Now let's find this. Okay, so we get f equals 500 Hz. Question 15b. The diagram below shows an experiment to measure the speed of a sound in a string. The frequency of the vibrator is adjusted until the standing wave shown in the diagram is formed, and we have this diagram. Okay, the frequency of the vibrator is 120 Hz. Calculate the speed at which progressive wave will travel along the string. So we are asked to find the speed. Okay, speed v equals what? Okay, so we are asked to find the speed, and the frequency f is 120 Hz. We can see, okay, in this diagram. Okay, we have two end, so this, and next is this end. So we are going to count the total number of standing wave formed between these two ends. So we have one complete wave. Okay, and this is another complete wave, clear, that is standing waves, and we have another complete standing wave. Okay, so altogether there are three complete standing waves. Okay, so we know this distance. Okay, this distance is called wavelength. So this is lambda, and this distance is lambda, and again this distance is lambda. So therefore we can write 3 times lambda equals 75 centimeter. Okay, so we can write lambda equals 75 by 3. So this gives 25 centimeters. So we have lambda equals 25 into 10 to the power minus 2 meter. So I'm writing in this way. Okay, 25 into 10 to the power minus 2 meters. So this is the wavelength. Okay, this is the wavelength. Now we are asked to find the speed, and we know speed equals frequency times wavelength, and frequency is 120 Hz. Okay, and wavelength is 25 into 10 to the power minus 2. Okay, now let's find this. So the speed is 30 meter per second. So this is the speed of progressive wave. Okay, that is 30 meter per second. Question number 16a, state Lenz's law in electromagnetism. So statement of Lenz's law. It states that the direction of induced current in a circuit is such that it always opposes the cause that produce it. So this is the statement of Lenz's law. Now let us discuss this. Okay, a magnet is quickly moved in a direction indicated by arrow between two coils C1 and C2 as shown in the figure. What will be the direction of induced current in each coil as indicated by the moment of magnet explained? So before understanding this question, let us discuss this. Okay, current carrying coil as magnetic dipole. Current carrying coil behaves as magnet. So if current carrying coil behave as magnet, then it must have two poles. So how we assign two poles in current carrying coil which behaves as magnetic dipole? So magnetic dipole mean that, okay, current carrying circular coil must have two poles. Clear? And magnetic dipole moment capital M equals N, which is number of turns, I, current flowing through the circular coil, and area vector A. So this is called magnetic dipole moment, or it is called magnetic moment, or it is called magnetic dipole moment, okay, for circular coil having n number of turns, okay, carrying current I, and having area of cross section, okay, vector A. So we have this. Now let us understand how we can assign, okay, magnetic poles to current carrying circular coil. Let's say current is flowing, okay, I is flowing in clockwise direction. So if we are watching from this side, okay, we are watching from this side, then the face towards the reader, okay, behave as south. So if current is flowing in clockwise direction, then the face towards the reader behaves as south. So the back side face, okay, the back side face behaves as north pole. So we have this, okay, and the front face, or the face towards the reader, or let's say the front face, okay, front face behaves as south pole. Now if we have current flowing in anti-clock direction, okay, let's say current is flowing in anti-clock direction and we are watching from this side, okay, we are watching from this side. So if current is flowing in anti-clock direction, then face towards the reader, or front face behaves as north pole, okay, this behaves as north pole, and the back side face, okay, back side face behaves as south pole. So we have this. So this is to be noted, okay. So if current flows in clockwise direction, okay, then the face towards the reader behaves as south, and if current flows in anti-clock direction, then the face towards the reader behaves as north pole. In this way, we can assign the direction, okay, or we can assign north and south pole to current carrying circular coil which behaves as magnetic dipole. Now let us consider this diagram, okay. So I'm drawing in this way. So I'm drawing in this way, okay. So there are few number of turns. This is coil C1, okay, and this is the next coil, okay, or I'm drawing over here. So this is coil C2 and the magnet is moved along this direction. So what we find, okay, it is moving towards C2 and is moving away, okay, from C1. So we are going to use the concept of Lane's law. We know we are moving magnet away. Let us consider this case, okay. Consider coil C1 and magnet moving away from C1. Now what we find from Lane's law, the induced current, okay, induced current in C1 is such that it opposes the cause. And what is cause? Cause is, okay, moving magnet away, which decreases the flux passing through C1. So as we know, induced current, okay, induced current in C1 is such that it opposes the motion of the magnet, okay. So what do you find? So induced current, so I'm writing in this way, okay. Therefore induced current in C1 flows in. Now what we find, induced current opposes the motion of the magnet which is away. So it tries to, okay. So in coil C1, okay, what we find in coil C1, what we find, it tries to pull the magnet towards C1. So induced current flows in such a direction that, okay, it pulls the magnet towards C1. For that reason, this phase of C1, that is coil C1, must behave as south. So if this phase behaves as south, then current in this phase must flow in clockwise direction. So induced current in this phase must flow in clockwise direction, okay. It must flow in clockwise direction. So current must flow, okay, I'm writing in this way. Induced current must flow in clockwise direction. So we find this, okay? So current must flow in clockwise direction. For this, the face towards the magnet must be south. So we have this. Now, I'm erasing this, okay? Now next, consider coil C2 and magnet moving towards C2. So what we find in this case, okay? In this case, flux through C2 increases, okay? Therefore, induced current in C2 opposes the increase in flux, or it opposes the motion of magnet towards C2. So what do we find? We find that when we move magnet, okay, towards C2, this is C2, okay, then induced current opposes this motion. It opposes inward motion. So in order to oppose this face, okay, the face of C2 towards the magnet must behave as south pole. So if this face behaves as south pole, then current, okay, that is induced current, okay, in this phase must flow in clockwise direction. So current must flow in clockwise direction. So what we find? What will be the direction of induced current in each coil? So direction of induced current in each coil, that is C1 and C2, will be clockwise. So it will be clockwise as indicated by the moment of magnet. So we find current in C1 and C2, okay, both will be clockwise. So we find this, okay, we find this. Justify Lane's law is in favor of principle of conservation of energy. So we want to verify this. So let us consider figure 1 and figure 2. So we have coil connected to galvanometer, okay, in figure 1 and 2. And let us take coil at rest, okay. So we have coil at rest, and in figure 1, magnet is moving towards the coil, okay. And in figure 2, magnet is moving away from the coil. Now, when the magnet is moved towards or away from the closed coil, induced current opposes the motion of the magnet. So this is in accordance with the Lane's law. Clear? Now, let us come to figure 1, okay. When the north pole of magnet is moved towards the coil, then what we find? In this case, the flux passing through the coil increases, okay. So why flux increases? Because we are moving magnet towards the coil. Now, the induced current, okay, the induced current set up in this coil opposes the increase in flux. That is, the induced current opposes the inward motion of the magnet. So inward motion is opposed. So for that reason, the face of the coil facing the north pole of the bar magnet behaves as north pole. Clear? It behaves as north pole. So if this face of the coil behaves as north pole and the opposite face or face back side, okay, this side behaves as south, then what we find, due to north and north, okay, there exists repulsion. So what we find is that repulsion is produced, okay, whenever we move magnet towards the stationary coil. So work must be done, okay, in bringing the magnet close to the coil against the force of repulsion. So we have this. Now let us come to figure 2. Now when the north pole of the magnet is moved away, so we are moving north pole away, okay, then what we find, the flux passing through the coil decreases. So why it decreases? Because we are moving the bar magnet away from the coil. Now the induced current produced in this coil, okay, opposes the decrease in flux. So it tries to increase the flux. That is, it pulls the magnet inward, okay. It pulls the magnet. The induced current, okay, opposes the motion. Since the magnet is moving in outward direction, the induced current, okay, opposes the motion of the magnet. That is, it pulls the magnet inward. So if it pulls the magnet inward, then what we find is that, okay, the induced current, okay, flows in such a way that the face facing towards the north pole of the bar magnet behaves as south and the opposite face behaves as north. So if this is south pole, then what we find, south and north, they attract, okay. So we find, okay, when we move magnet away from the coil, then the induced current flows in such a way that the face facing towards the north behaves as south. So there exists force of attraction. So work must be done against, or what must be done in moving the magnet, okay, away from the coil. We want to move magnet away, and okay, due to south pole on this face, okay, it pulls the magnet inward. So work must be done in moving magnet away from the coil against the force of attraction. So it is found that, okay, it is found that it is this work done. So we are doing work done. So in this case, okay, we are doing work done against the force of repulsion, or work has to be done against the force of repulsion. And in this case, work has to be done against the force of attraction. So it is this work done against the force of attraction or repulsion that appears as electric energy in the form of induced current. So work done appears, okay, as electric energy. So we can conclude that Lenz's law supports the law of conservation of energy. Question 17a, state the principle of potentiometer. A potentiometer is also called voltmeter of infinite resistance. Why? Now let us discuss the principle of potentiometer. Potentiometer is based on the principle that potential drop or fall in potential, okay, potential drop across any length of the potentiometer wire is directly proportional to the length of that portion of the wire, okay, provided, so this is the condition, okay, provided that current, cross-sectional area and composition of the wire is constant. So potentiometer is based on this principle. So we can write in this way, okay, mathematically, potential drop V is directly proportional to the length. So V equals constant K times L. So we can write K equals V by L. Okay. K, this is constant of proportionality. Okay. And we can see from this equation, K equals potential drop per unit length. So it is called potential gradient. So we have this. Now, let us discuss, okay, the second part of this question. A potentiometer is also called voltmeter of infinite resistance Y. So I'm writing a potentiometer is also called voltmeter of infinite resistance because it do not draw. So this is to be noted, okay? It do not draw any current from the source of EMF at null point. So this is to be noted. Question 17b. In the meter bridge experiment, the balance point was observed at J with L equals 20. The value of R and X were doubled and then interchanged. What would be the new position of balance point? If the galvanometer and battery are interchanged at the balance position, how will the balance point get affected? We need to note that, okay, meter bridge works on the principle, okay, on the principle of Wheatstone bridge, okay. So this is to be noted. So we have to design Wheatstone bridge circuit for this given circuit, okay. So for this given circuit, we need to design Wheatstone bridge circuit, okay. So we need to note this. Now I am redrawing, okay, this figure in magnified scale, okay. So this is R, this is X, this is A, so this is B, point B, this is B, and we have battery between A and B, and we have galvanometer, okay, connected in this way. This is jockey J, okay, and this length is L, and L equals 20 centimeter, and the remaining length, okay, this is 100 minus L in CGS system, because we know length AB equals 100 centimeter or 1 meter, okay. Meter bridge, okay, have wire of length 1 meter or 100 centimeters. So we find this and let us design woodstone bridge circuit. Okay, so I'm drawing over here. I'm not using key. Okay, this point is A, this is B. Now let us call this point, okay, C, and this point as D. So this is C and this is D. I can call this D and this point as C also. Okay, so we have galvanometer between C and D, and I'm not using key, okay, as I said earlier. So we have this. Now we have resistance R between A and C, resistance X between C and B, and we need to find the resistance of the length AD. That is, we need to find this resistance, and we need to find the resistance DB, okay, of the wire. So that is, we need to find this resistance. So for that, what we do is that let R, okay, be the resistance per centimeter of the wire AB, okay. So we have this. So what do you find? R has unit resistance per cm, okay. So this is to be noted. So therefore, resistance of length AD, okay, we are finding the resistance of the length AD. Length AD equals L times R, because when we multiply L with R, we know L is in centimeter, okay, and small r is resistance per centimeter. So this product, okay, has unit ohm, that is, it has unit of resistance. So we are changing length into resistance. So the resistance of AD is LR, okay. And resistance of length DB, this is 100 minus L times R. So we have this. Now, so I'm writing in this way, 100 minus L times R. Now, at balanced condition, okay, of woodstone bridge, what we get? The ratio R by X equals the ratio LR by 100 minus L times R. So this cancels out. Therefore, we can write R equals, okay, from this equation on simplification, L by 100 minus L, and we have X. So let us call it equation 1. So we have this. Now next, what do we have? The value of R and X were doubled. Now R and X is doubled, okay. So R and X is doubled and interchanged. So now we have twice X, okay, and twice R. So we are asked, what will be the new position of the balance point? So I'm erasing this, okay. Now let's say let's say the new position of the balance point is this. Okay, let's say jockey is at this position, and let the new balance point be at distance L dash. Okay, it is at distance L dash from point A. So the remaining distance, okay, is 100 minus L dash. Okay, so we have this 100 minus L dash. So we have this. Okay, so this is the position of jockey. So we need to note this. Okay, so we have this. So what do you find now? We find R and X, okay, are doubled and the position is interchanged. So now we have this. Okay, we have twice X between A and C and twice R between C and B. Okay, so I'm writing in this way. Okay, let L dash, okay, this is the new balance length. Okay, so this is the new balance length. So we have this. So let us write in this way. R and X are doubled and interchange. Then let the balance point be at distance L dash from point A. We always slide jockey from A because it is at high potential, then B. Okay, so this is to be noted. Now, as we did earlier, okay, so the resistance of AD is now L dash times R, and this DB has resistance 100 minus L dash times R. So we have this. Now at balance condition, okay, so I'm writing over here. At balanced condition, we get the ratio twice X by twice R equals the ratio L dash R by 100 minus L dash times R. So this R and R cancels out, 2 cancels out. Therefore, we can write X equals L dash by 100 minus L dash, and we have R. Okay, so we get this. Let us call it equation 2. So we have this. Now, I'm erasing this. Okay, now from 1 and 2, okay, 1 and 2, we are going to put the value of R from equation 1 in equation 2. So what do you get? X equals L dash by 100 minus L dash, and the value of R is L by 100 minus L, and we have X. So we get this. So X cancels out. Okay, so we can write 1, okay, equals L dash L by 100 minus L dash, and we have next 100 minus L. Now let us do calculation. Okay, so I'm erasing this. So on simplification, okay. So this cancels out, okay. So on rearranging, you can take 100 common on right hand side. So what we get now is that 100 equals L plus L dash. Therefore, L dash equals 100 minus L. So we get this. Okay, so we are getting it. Now, L dash equals 100 minus L, and L is 20, okay. So L dash equals 80 centimeter. So we are asked to find what will be the new position of the balance point. So the new position of the balance point is at 80 centimeter from point A. So this is to be noted, okay. Now next, if the galvanometer and battery are interchanged at the balance position, how will the balance point get affected? So if, or let me write in this way, okay. Changing the position of galvanometer and battery at the balance point will not change, okay. So this is balance position, okay. At balance position will not change the balance point. So this is to be noted, okay. Or A, state the two Kirchhoff's law for electrical circuit. To understand Kirchhoff's law for electrical circuit, you can see my lecture video of Kirchhoff's law. The link is added on the description. Now let us come to this, okay. In meter breeze shown below, the null point is found at distance 60 centimeter from A. If now a resistance of 5 ohm is connected, okay, is connected in series with S, the null point occurs at 50 centimeter. Determine the value of R and S. So we know meter breeze, okay, works on the principle of Wheatstone breeze. So we need to design Wheatstone breeze of this given circuit. So at first what we do, case 1, okay, without 5 ohm, okay, because we find resistance 5 ohm is connected in series with S. Now I'm redrawing this diagram, okay. So we have battery and key, okay? And we have a meter scale. So there is a scale. So this is a scale, okay? So we have this, okay? And we can see A is connected to positive a battery and B is connected to negative a battery. So for that reason, we slide jockey from A to B, okay? So I'm writing we slide jockey from A, which is at high potential, to B, which is at low potential. So this is to be noted, okay? So this is jockey, and let this point be D. And what we find, okay, in meter bridge below, the null point is found at distance 60 centimeter from A. So this distance, okay, so this distance is L, and L is 60 centimeter. And the remaining distance, okay, remaining distance is 100 minus L, and this equals 40 centimeter. So we have this. So this is to be noted, okay. Now let us design Wheatstone bridge for this given circuit, okay. So I'm drawing over here. This is A. This is B. We have key. So I'm not taking key, okay. Let's close the key, because in original experiment we have tap key, okay. Now let's call this point, okay. Let's call this point C. So this is C. So this is C, and this is D. We have galvanometer between C and D. Now we have resistance R between A and C, resistance S between C and B. Now we need to find resistance of the length AD of the wire, and we need to find resistance of the length dB of the wire. So we need to find these two resistance, okay. So as we did earlier, let R, this is resistance per centimeter of the wire AB. Therefore we can write resistance of length AD equals L time R, okay. So if we multiply L with small r, then the product has unit of resistance, okay. So this is to be noted, and we did it earlier also. And so we can write in this way, L times R, and resistance of length dB equals 100 minus L times R. So we have this, okay. Now what we get at balanced condition, at balanced condition of Wheatstone bridge, okay, we get this ratio R by S equals ratio LR by 100 minus L times R. So this cancels out, okay. So what we get is that, so I'm writing over here, R by S equals L by 100 minus L. So we have this. So we are getting this, okay. Now what we find, L is 60, okay? So R by S is 60 by 100 minus L is 60. So 100 minus L, that is 100 minus 60. So this gives me 60 by 40. So we get this 3 by 2. Therefore, R by S equals 3 by 2. So without 5 ohm in series with S, okay, we get this equation or result. So let's call it equation 1. So we have this. Okay. Now next what we do. So I'm erasing this. Okay. Now I'm erasing this also. So we get this. Okay. R by S equals 3 by 2, and let's call it equation 1. So we have this. Now let us consider case 2, okay, with 5 ohm connected in series with S. So we are going to discuss this. Okay. Now I'm redrawing this circuit, okay, with 5 ohm in series with S. We have same meter bridge, okay. This is S and this is 5 ohm. We have R. So this is C. This is B. This is A. Now what we find, on connecting 5 ohm in series with S, the null point occurs at 50 centimeter. So we find the total length is 100 centimeter, okay. Length AB equals 100 centimeter. So we get null point at exactly midway of AB. So this is jockey, okay. So let's call it D. So L is, let's say this is L dash, this is 50 centimeter. So the remaining length 100 minus L dash, this is also 50 centimeter. So we have this, and we have battery, okay, and we have key. So I'm closing key, okay. So we have this, and we have a scale. So this is scale. So we have this. So what we find, on connecting 5 ohm, the null point shift towards A. So initially we were having L equals 60 centimeter. Okay. Now the null point is shifting towards A. So we are getting null point at distance L dash equals 50 centimeter from point A. So we are getting this. Now these two resistance are connected in series. Okay. So it is connected in series. So we have this, okay? So this is to be noted. Now let us draw Wheatstone bridge, okay, for this. This is B, this is A, this is C, this is D, and we have galvanometer, okay? We have battery between A and B, and I'm not drawing or taking key, okay? Now we have R between A and C, and we have resistance S plus 5, okay? They are connected in series, and we have resistance, okay, as we did earlier. Resistance of AD equals L dash times R, because R is resistance per cm of the wire AB, and R, okay, is constant, okay, for wire AB, and the resistance of DB is 100 minus L dash times R. So we have this. Now at balance condition, okay, what we do? So I'm writing over here, at balanced condition of Wheatstone bridge. Wheatstone bridge, okay, we get this, okay, ratio. We get ratio R by S plus 5 equals L dash R by 100 minus L dash times R. So we have this. So we get this. Okay. Now this R and this R cancels out. Okay. So what we get now? So I'm writing over here. R by S plus 5 equals L dash by 100 minus L dash, and we find L dash is 50, okay? So we can write R by S plus 5 equals 50 divided by 100 minus 50. So finally we can write this, okay? 50, so this cancels out. So we get this, okay? So I'm erasing this. So we get R by S plus 5 equals 1. Therefore, we can write R equals S plus 5. Now, let's call it this equation, okay? So, we have this equation. Now, what we do? From equation 1, okay, we have R equals 3 by 2 S. So, we are going to put this value in this equation. So, if we put it, then what we get, okay? So, R equals, from this two equation, okay, this and this equation, R is 3 by 2 S equals, we have S plus 5. So let us simplify it. 3 by 2 S minus S equals 5. Therefore, we can write 3 by 2 minus 1, and we have S outside the bracket. This equals 5. So this will give me 1 by 2, S equals 5. Therefore, S equals 10 ohm. Okay, so we have this. So if S is 10 ohm, okay, because we are asked to find the value of S. So S is 10 ohm, okay, so this is to be noted. Now we can find the value of R from this equation. So R is 3 by 2 times 10. So R is 15 ohm. So the value of R, okay, R is 15 ohm. So we get this. Question number 18. The graph below shows the maximum kinetic energy of the emitted photoelectrons as the frequency of incident radiation on a sodium plate is varied. Now we are asked to find from the graph determine the maximum frequency of the incident radiation that can cause photoelectric effect. Next, calculate the work function for sodium. And next, use the graph to calculate the value of Planck's constant in Joule second. So I'm drawing the diagram, okay? We have sodium plate. This is sodium plate, and we have incident, okay? This is incident radiation. Incident radiation, and let its energy, okay, be HF, or we can also use this symbol, okay? Energy of photon equals H nu. Okay, this is the Greek letter nu. So I'm using this symbol, okay, HF. Now some part of this energy of the incident radiation is utilized, okay, to eject electron from the sodium plate, and that amount of energy is called work function, okay? So let W naught be the work function of the sodium, okay? So we are asked to find the work function for sodium, and the remaining energy is taken by photoelectrons, okay? So the remaining energy is taken by photoelectrons in the form of kinetic energy. So let the kinetic energy be Kmax. So the electron takes rest of the energy in the form of maximum kinetic energy. So we have it. Okay, so we have this. Now what we do? If you see, so let me write first the equation, okay? The energy of incident radiation or photon is divided into work function and the maximum kinetic energy of the photoelectron. So that is HF equals W naught plus maximum kinetic energy. So let's write in this way, okay? Delta Kmax. So this is the equation we are going to use, okay? Now let us come to this graph, okay? So what do you find in this graph? So this is the horizontal, so I'm extending this, okay? And this is vertical. Let's say this is vertical, and let's say this is X and this is Y, okay? Y. So what do you find? This, okay? 1, 2, 3, 4, 5. So what do you find? 5 small division along X axis equals 2 into 10 to the power 14 Hertz. So we have frequency expressed in Hertz, okay? So one small division along X-axis equals 2 into 10 to the power 14 divided by 5 So it is in Hz. Now let's see. We need to count the number of division along X because we have graph, okay, in this way. So 5 and this is again 5. So we get 10, 10, 11, 12, 13, 14. So 14 small division along x-axis equals, so we have this, okay, simple calculation, 14 times 2 into 10 to the power 14 divided by 5. So this is Hz. Now let's find it. So we get this, okay. So this equals 5.6 into 10 to the power 14 Hz. So therefore, the minimum frequency, okay, actually it will be the minimum frequency of the incident radiation that can cause the photoelectric effect is called threshold frequency. So what we know is that minimum frequency, so we can see this is the minimum frequency, okay, of incident radiation that can cause photoelectric effect is called threshold frequency and is denoted by the symbol F0. So this is the threshold frequency. So the threshold frequency is F0 equals 5.6 into 10 to the power 14 Hz. So from the graph, we need to determine the minimum frequency, okay, at which photoelectric effect occurs. So A, threshold frequency, F0 equals 5.6 into 10 to the power 14 Hz. So we found it from the graph, okay, or we find it from the graph. Next, we need to find the work function, okay, for sodium. And work function W naught equals H, that is Planck's constant, times the threshold frequency. And we have threshold frequency, therefore we can write W naught equals, now Planck's constant is, so I'm writing over here, H is 6.63 into 10 to the power minus 34 joules second, okay. So this is the value of Planck's constant. So 6.63 into 10 to the power minus 34, okay, joules second times F naught, and F naught is 5.6 into 10 to the power 14 Hz, and we can simply write Hz in this way, 1 by second, okay. So we have this. Now this second and second cancel out. So work function is the energy required, okay, to liberate the electron from the metal surface, okay. So let us find this, okay. So we get this 3.71, okay, 2 into 10 to the power minus 19 joule. So we are getting W naught, that is work function, equals 3.712 into 10 to the power minus 19 joule. Now we can change joule into electron volt. We can express work function in electron volt, and we know, okay, this we know 1 electron volt equals 1.602 into 10 to the power minus 19 joule. So let us convert work function into electron volt. Okay, so what we do, W naught, and we know 1 joule. Okay, from this equation we know 1 joule is 1 by 1.602 into 10 to the power minus 19 electron volt. Okay, so we have this. Therefore, from this equation, okay, W naught equals 3.712 into 10 to the power minus 19 electron volt divided by 1.602 into 10 to the power minus 19. Now let us find it. Okay. So we get this, okay. Work function W naught equals 2.317 electron volt. So this is work function in joule, and this is work function in electron volt. So we have this. Now we are asked to find, use the graph to calculate the value of Planck's constant in joule second. So we need to find it, okay. Now I'm erasing this, okay. And this is the standard value of Planck's constant, okay. Now we are asked to find the value of Planck's constant in joule second from the graph. So let us take this relation, okay. As I said earlier, work function W naught, this is Planck's constant times the threshold frequency. So what we get from this equation, HF equals HF naught plus delta K max, okay. So on rearranging, we can write HF minus HF naught equals delta K max. So I can take H common and write F minus F naught equals delta K max. So let us denote, okay, this difference F minus F naught by the symbol delta F, okay. So let us use this. Therefore we can write H times delta F equals delta K max. Therefore Planck's constant, okay, we can write. So Planck's constant, so let me write in this way. Therefore Planck's constant H equals delta K max divided by delta F. So we are going to use this relation in this graph to determine the value of Planck's constant. So Planck's constant equals change in kinetic energy, that is maximum kinetic energy, by change in frequency. So we need to find the slope. See, we have kinetic energy, that is maximum kinetic energy along y, and we have frequency along x. So now I'm erasing this also, okay? Now let us take this, okay? This part of the graph. Let us take this part of the graph. And find the slope, okay? And find the slope. So what we do is that, okay, let us find first delta F. So delta F is, see, I need to take this one this point and another this point. So 10. So we know delta F is F minus F naught, okay? 10 minus 5.6 into 10 to the power 14 Hertz. Okay? So this gives me the value 4.4 into 10 to the power 14 Hertz. Now, let us find this height, okay? So I need to count how many division, okay, is there from this point to this point. So you can see 1, 2, 3, 4, 5. So this gives me 5. This is another 5. This is another 5. So, and there is 1, 2, 3. So it means 5 plus 5, okay, plus 5 plus 3. So all together you find there are, okay, you find 15 plus 3, 18 division. 18 division, okay, maximum 18 division along y. So we find this, okay. So what we do is that 5 small division along y equals 0.5 electron volt. So one small division along y equals 0.5 divided by 5 electron volt, and there are total 18 divisions, okay. The total maximum 18 divisions. We need to take maximum 18 division, okay. So total there are 18 small division along y equals 18 times 0.5 divided by 5 electron volt. So let us find this. So we have 18 times 0.5. Okay, this divide by 5. So we get 1.8. So this gives the value 1.8 electron volt. So this point corresponds to kinetic energy, which is 1.8 electron volt, and this point corresponds to kinetic energy, that is 0 electron volt. Okay, so therefore delta Kmax equals 1.8 minus 0. So this gives 1.8 electron volt. So if we find the slope of this graph, okay, from graph, okay, if we find the slope, let's find the slope. So what does the slope of the graph gives? Slope of the graph, let me write in this way. Slope of the graph gives, as I said earlier, it gives Planck's constant h. Therefore, h equals delta Kmax by delta F equals 1.8 electron volt divided by 4.4 into 10 to the power 14 Hertz, and I'm writing in this way, okay? For frequency, I'm writing in this way. Now, let us find this, okay? We know 1 electron volt because we want Planck's constant in joule second, and we know 1 electron volt is 1.602 into 10 to the power minus 19 joule, okay? So we have this. So let's convert this also. So H equals 1.8 into 1.6 in 1.6602, okay, into 10 to the power minus 19. So we have joule, and this second will move up. So we have joule second divided by 4.4 into 10 to the power 14. So let's find it. So we get this. H equals 6.55 into 10 to the power minus 34 joule second. So we get this, okay? So the value of H, the value of Planck's constant. So this value, H equals 6.55 into 10 to the power minus 34 joule second, okay? And this is from the given graph. So we have this. Question 19a, figure below shows the experimental setup of Millikan's oil drop experiment. Find the expression for a charge of an oil drop of radius r moving with constant velocity v in downward direction using free body diagram. So we have this experimental setup. In order to understand Millikan's oil drop experiment to determine charge of an oil drop in more detail. You can see my lecture video. The link is added on the description. Now let us come to 19b. What will be the expression for the charge of an oil drop if the electric force is greater than its weight? So I'm drawing these two plates, okay? This is upper plate and it is positively charged, and we have lower plate which is negatively charged. And let us consider, okay, or we take negatively charged oil drop. Now since upper plate is positive and lower plate is negative, so we find electric field acting in downward direction, okay? So due to this, electric force, okay, Fe acts in upward direction. So I'm writing electric force in magnitude. Now the weight of the oil drop, that is W equals mg, acts vertically downward. And since the oil drop is negatively charged and upper plate is positive, so that the motion of the oil drop is vertically up. So let it moves with velocity v in upward direction, okay? So we have this. Now, the buoyant force due to air, okay, is Fb, and we can see buoyant force is opposite to weight. And since the motion is upward, okay, the resisting force Re, okay, so Re is the resisting force acting in downward direction. It is opposite to motion. So Re is the resisting force, okay, in the presence of electric field. So we have this. So I'm redrawing this figure over here, okay. So electric force and buoyant force, okay, are acting in upward direction, and weight equals mg is acting in downward direction. And since the motion, okay, the motion is upward, okay, it is moving in upward direction. So let me write in this way. Motion is upward and let it move with velocity v in upward direction, so that the resisting force Re is in downward direction. So this is buoyant force due to air, and this is resisting force. So this is to be noted, okay. Now we know resisting force Re equals some constant times the speed, that is v, and constant k according to Stokes, okay, is 6 pi eta r. So this is according to Stokes, okay. Therefore we can write Re equals 6 pi eta r v. So we have this. Clear? We have this. Now let us find the total force, okay, or the net force. So the net force in the presence, okay, in the presence of electric field is F equals Fe plus buoyant force, okay, Fb, clear, minus Re minus mg. We can also write buoyant force by this symbol, okay, capital B. You can use this symbol also. So I'm writing over here Fb. We can use this symbol. Now what we find or we can write in this way. Total force F equals Fe plus Fb minus mg minus Re is 6 pi eta Rv. So we have this. Okay. Now, when the drop attains terminal velocity, let's say Ve, okay, in the presence of electric field. So I'm writing in this way, okay, that is when V equals Ve, terminal velocity in the presence of electric field, then F equals 0. Net force is 0. Therefore, from this expression, okay, from this expression we can write 0 equals Fe plus Fb minus mg minus 6 pi eta R Ve. So we have this. Now, what we find from this question is that electric force is greater than its weight. So I'm writing in this way, okay, Fe minus mg, okay, plus Fb minus 6 pi eta Rve. So what you find, if electric force is greater than mg, then this difference Fe minus mg is approximately, okay, Fe. So we can write 0 equals Fe plus Fb minus 6 pi eta Rve. Now, we can write in this way, okay, Fe plus Fb equals 6 pi eta Rve. We are asked to find the expression for charge on an oil drop, and we know Fe, electric force, okay, this equals Q times electric field. Therefore, we can write QE plus Fb equals 6 pi eta Rve. Now, if we neglect, okay, if Fb is neglected, okay, let's say we are neglecting buoyant force, okay, then what we get, QE equals 6 pi eta Rve. So we get charge Q equals 6 pi eta Rve by electric field. So this is the expression for electric field when electric force is greater than the weight of the charged oil drop. 19C, determine the electric field when the electric force applied between the two horizontal plates just balances an oil drop with 4 electrons attached to it and mass of oil drop is 1.3 10 to the power minus 14 kg. So we have number of electrons, okay? So I'm writing number of electrons, small n equals 4, and we are asked to determine electric field. Electric field, capital E, this is unknown, so we are going to find it. And mass of oil drop, M equals 1.3 10 to the power minus 14 kg. So we have this, okay, given from the question. And we have this condition, okay, electric force applied between the two horizontal plates just balance an oil drop. So what do we find? So This is upper plate, okay, and this is lower plate. So we have oil drop. So at balance condition, okay, electric force equals weight. So we have this. So this is weight of oil drop. So what do you find? Okay, at balanced condition, okay, we find this electric force, okay, equals weight of oil drop, that is W. And we know electric force equals Q times E, and we can write in this way, okay, n small e times capital E, because we know Q equals NE, where N is the integer, okay, and small e is charge on single electron. So small e equals 1.6 10 to the power minus 19 coulomb. This is charge on single electron. So we can write, okay, electric force equals N small e capital E equals weight, and weight equals mg. So we are asked to find electric field, that is capital E. So this equals mg by Ne. M is mass of oil drop, and we have 1.3 into 10 to the power minus 14, and G is 9.8, okay, in SI, divided by N, and number of electrons is 4, so N is 4, and small e is charge on single electron. So let's calculate this, okay. So we get this numerator is 1.274 into 10 to the power minus 13. So 6.4 into 10 to the power minus 19. So let's find it. So we get this, okay. 199,062.5, and the unit is volt per meter. Therefore, the magnitude of electric field, okay, is 199,062.5 volt per meter. So we have this. Question number 19, or a diode can be used as a rectifier. What characteristics of a diode is used in rectification? We need to understand first what is rectifier, okay? So the process of converting alternating voltage into direct voltage is called rectification, and the device used For this purpose is called rectifier. So this is the concept of rectifier. Okay. Now, what characteristics of diode is used in the rectification? So let us consider. Okay. Let us consider PN junction diode. Okay. So I'm erasing this. Now, when PN junction, okay, is in forward bias, clear, it offers negligible or very less, okay, it offers negligible resistance, due to which current, okay, due to which current flows through it. Now, when, so I'm writing over here, when PN junction, okay, when PN junction is in reverse bias, it offers high resistance, due to which negligible, okay, due to which negligible current flows through it. So what we find in forward bias, current can flow or pass through PN junction diode easily, whereas in case of reverse bias, negligible or almost no current flows through the PN junction diode. So this unidirectional property, okay, so I'm writing over here, this unidirectional property or characteristics, okay, of diode, so PN junction diode is used in rectification, okay. So we have this. Now, let us come to this circuit, okay. We can see this circuit is made from NOR gate. This is NOR gate, and we have AND gate, okay. This is AND gate, and we have NOT gate. So this is NOT gate, okay. So this is another NOT gate. So we have this. Now, let us discuss the truth table for OR, NOR, and NOT gate. So this is OR gate, and we can see if there is NOT, okay, on OR. So if there is not on OR gate, then it is called NOR gate. So this NOT, okay, this NOT gives inversion, okay, or it inverts the output. So this is to be noted, okay. Now, if A is 0, B is 0, so that is if we have low on A and B, then we get Y 0, that is low. And if A is 0 and B is 1, that is high, then the output Y is high. And if we have this, okay, if A is 1, that is high, and B is 0, that is low, then again the output Y is high. And if both inputs, that is A and B, is high, then we get output high. So we have this. Now NOR, okay, so NOR, this is not plus OR, clear? So the output for 0 0 is high, that is 1, and for 0 1, you can see in OR gate we have 0 1, and for 0 1 the output is high. Now in this case we get low, that is 0, and 1 0 we again get what? Low, and for 1 1 we get low, because it inverts, this not inverts the output. Now for AND 0 0, this is 0, okay, 0 1, this is 0, 1 0, this is 0, 1 1, this is 1. So we get output high only when both the inputs are high. So when both inputs are high, then we get high output. So this is to be noted, okay. Now for this NOT. Now if A is low, then the output is high, that is 1. And if A is high, that is 1, then we get output low. So with these idea, okay, we are going to construct truth table for this given circuit, okay. So I'm erasing this. Now let's see. So I'm writing in this way: if A is 0, okay, and B is 0. Now what do you find? We have 0, okay. Now this 0, okay, will finally change into 1, okay, after passing through this NOT gate. So if B is 0, A and B is 0, then C is 1, and B is 0, so we have 0 over here, and D is 1, okay, because it inverts 0 and we get 1, so D is 1, here. Now this is AND gate, and 0 and 1 will give us 0, so D is 1, C is 1, and E is 0. What about F? Again for 1 0 we have 0, so we get 0. Now we have NOR gate, okay. So what we are getting? We are getting 0 and 0, and for 0 0, okay, we get 1. So we have this. So we are asked to state E, F, and G. So what we are getting? A is 0, F is 0, and G is 0 for A0, B0. Next, now if A is 0 and B is 1, okay, A is 0 and B is 1. So we have 1 over here, and we have 0. Now this 0, okay, on passing through this NOT gate, So it will change into 1. So C is 1 and 1 will change into 0. So D is 0, okay. So 1 on passing through this, or high on passing through this NOT gate will change into 0, and 0 0 will give us 0. So A is 0. So A is 0. Now 1 1 will give 1. So F is 0. So we get this. So A is 0, F is 0. Now what about G? We see if we have 0 1, okay, then we get, if we have 0 1, then we get output 0. So we get 0. So we are getting this, okay. So we are getting this. A is 0, F is 0, G is 0 when we have 0 1. Now next, A is 1, B is 0. Now A is 1 high and B is low, that is 0. So we have 0 over here. Now we have 1. So this high on passing through this NOT gate will change into low, that is 0. Now this low or 0 on passing through this NOT gate will change into high, okay. Now for this AND gate, E is high, okay. Now for this AND gate, okay, 0 0 gives 0. So what do we get? C is 0, D is 1, E is 1, F is 0, and for 1 0, okay, 1 0 we get 0. So we get 0. So what we are getting? We are getting E1, that is high, F0, that is low, and G0, that is low when we have A1 and B0. Now A1, B1, both high, okay, both inputs are high. So 1 1, so we have 1 1. Now this high on passing through this NOT gate will change into 0. So we have C0, and this high, that is 1, on passing through this NOT gate will change into 0, that is low. So we have D0. Now for this AND gate, okay, 1 0. So 1 0 will give 0. So A is 0. And for this gate, okay, AND gate 0 1, 0 1 will give 0. So we have E0, F0. Now for 0 0 we get high, okay. So we have 1. So what we are getting? We are getting for A1, that is high, B1, that is high, E is low, that is 0, F is 0, that is low, and G, that is output, okay. Final output of this circuit is 1, that is high. Draw a circuit diagram of full wave rectifier. So this is called center tap transformer, okay. In case of full wave rectifier, there are two diodes. Okay, so this is diode D1 and this is diode D2. And there is load resistance RL. Okay, so this is load resistance, and this, okay, represent center tap. So this is the circuit diagram of full wave rectifier.